Okay, let's take a look at source transformations in frequency domain, and specifically let's look at this circuit where we're asked to calculate Vx, which is the voltage across this resistor here, using the method of source transformations. Okay, just like we did source transformations in the time domain, we're going to do the same thing here, and the idea is you take in this case this voltage source combined with this impedance or resistance here, and you're going to convert it. So you have this voltage source with some impedance, and you're going to convert it to a current source in parallel with some impedance. So first it's you got something in series, and then you're going to make it a current source in parallel with the impedance, and then you go back and we can go back and forth between these two. So you can, if you have a current source with some impedance in parallel, you can convert it to a voltage source with some impedance in series, and that's what we're going to do in this problem. Okay, so let's go ahead and do this. So we have this voltage source that's in series with this impedance, the 5 ohms. So we're going to convert it to a current source in parallel with that 5 ohms. So if I do that, we do the calculation, it's just going to be Is is equal to the voltage source divided by the impedance. In this case, our impedance is 5 ohms and our voltage source is this guy. So Is is going to equal to 20 minus 90 degrees over that 5 ohms. Okay, and then that's really going to be 4 at minus 90 degrees. We can convert that into rectangular format, and that's going to be minus J4 amps. So that's how we get that. And then if we redraw the circuit, come down here, I'm going to just bring this up so you can see it, and we can redraw the circuit where now we have our transformed. So we're using our source transformation. Now we have a current source, which is minus 4J, and then we keep that resistor there. Okay. Next, what we can do is we can combine some of these impedances, and what we can do is we can combine the, I'm going to do this here, we can combine these 5 ohms with the 3 ohms and the J4 ohms there. So those guys in series, and we can combine all 3 there and call this Z1. So we can make this Z1. Okay, so let's do that. So we're going to say Z1 is equal to 5 times 3 plus J4, because they're in series, over the sum of those, which is going to be 8 plus J4, and that's going to give us 2.5 plus J 1.25, and that's ohms. So now we have Z1. Okay. Next, what we're going to do is, now that we have Z1 defined for that section, we can combine, we can convert back from the current source to a voltage source, and to do that we have to go back to this guy, and we know that Vs is just going to be Zs times Is. Okay, so we're going to say our voltage source is going to equal to Is times Z1 in this case. Okay, so which is going to be minus J4 times 2.5 plus J 1.25, and that's going to give us 5 minus J 10 volts for Vs. So now we have our Vs here is going to be here, can redraw the circuit here. So we got our 10 ohms is here, minus 13J, 4 ohms. We got J 1 to 5 and then 2.5, and now we've got our Vs as 5 minus J10. Okay, so let's go ahead. So this 2.5 in J is really, let me go ahead and highlight this. Our Z1 is really going to be this guy here. And now we can solve for Vx by voltage division. So we can use voltage division to get Vx, which is going to equal to, let's go up here, you can see the circuit, 10 over 10 plus 2.5 plus J 1.25 plus 4 minus J 13, all of that times the source, which is going to be 5 minus J10, and that's going to equal to, if we do the math, 5.519 at an angle of minus 28 degrees, and this is volts. So this is how we come up with our final answer for the Vx. Okay, again, very simple source transformations, and remember, the key to source transformations is to be able to jump back and forth between a voltage in series and a current in parallel with some impedance, and we did that twice in order to simplify our circuit and to come up to solve for our Vx here. Okay, and that's it for this problem.